A limit is the y value of a function, f of x, that a graph approaches as the x value becomes closer and closer to some given value. That's pretty standard definition there. Let's get some notation down, just kind of learn how to write this stuff before we jump into any kind of crazy looking problem. To start with, this left-hand limit, this is the limit of f of x as x approaches c from the left. So let's write this. The limit as x approaches c from the left. Okay, so that's the negative sign up there. This little positive sign right here is the same thing, except it's going to be from the right. Notice it's from the right, from the left, from the left, from the right. And this last one is just the limit as x approaches c. Okay. All right, so we're going to use this graph from the other day. That's on your notes, I think from the other side of the sheet of paper. We've got this function, we've got some asymptotes, got a hole right there. So when we're doing these problems down here, we're looking up here at this graph. Okay, so we have an old way of writing this stuff, and this is just in behavior. As x approaches negative infinity, the graph of f of x does something. Okay, so if we look up here, as x approaches negative infinity, as we're going this way on our graph, the y value is approaching what? Looks like my dotted line is at 3, so I'm going to come up here. F of x approaches 3. And the new way of writing that would be the limit as x approaches negative infinity of f of x equals 3. Next one, I've got, as x approaches infinity, the graph of f of x is, so as x approaches positive infinity, the graph is getting closer and closer to 3. Getting closer and closer to 3. So we'll write this as the limit as x approaches infinity of f of x equals 3. Okay. As x approaches negative 3 from the left, the graph of f of x. Okay, so let's look up here. As x approaches negative 3 from the left, notice we're coming over here from the left. We're getting closer and closer to this negative 3 right there. The graph is going towards infinity. Okay, so I would write it like this. The limit as x approaches negative 3 from the left, put the little minus sign up there, of f of x equals infinity. Okay. As x approaches negative 3 from the right. As x approaches negative 3 from the right, all right, as x approaches, there's negative 3. As it comes from the right side, looks like it's going to negative infinity. Negative infinity. Okay. So we're going to write that as the limit as x approaches negative 3 from the right, little plus sign, of f of x equals negative infinity. Okay. All right, as x approaches 3 from the left, so just that would be limit as x approaches positive 3 from the left would be a minus. The graph of f of x does something. All right, let's look up here. as x approaches 3, all right, this is the weird one, it's got a hole right there. As x approaches 3 from the left side, so we're going to start over here and we're getting closer and closer and closer to that 3 right there. What is my y value going to be? Well, on the previous problem, we said that the hole was at, I believe we said 3 5/3 or 1.66666. So my y value right there would be 5/3. So as we're coming from the left, we get closer to 5/3 right here. And next one, so as x approaches 3 from the right, so we're coming from this direction now. As I get closer and closer to 3, what number am I getting really, really close to? That 5/3 again. So limit as x approaches 3 from the right of f of x equals 5/3 as well. Now, that's different than saying, what does, if I had said, what does f of 3 equal to? That's undefined. There's a hole right there. That's undefined. But if we're looking at a limit, a number that we're getting really, really close to, then the number we're getting really, really close to as we get from the left, we're getting really, really close to this y value of 5/3. And as we're coming from the right, we're getting really, really close to this y value of 5/3. Doesn't have to equal it right there. That's undefined. But we're getting really, really close to that number. All right, let's check out one of these graphs down here. So looking at this graph, we're going to answer some of these questions. We're not going to do all these, but some of them more so are the one-sided ones. All right, so there's my graph. It's got some crazy stuff going on, like there's a dot up there, there's an open circle right there, maybe something like a quadratic right there. Anyways, all right, we've got the limit as x approaches 2 from the left. As x approaches 2 from the left. So let's look at the graph. As x approaches 2 from the left side. So as I'm coming over here and I'm getting closer and closer to that 2, what's my y value going to be? -1. As I'm getting closer and closer to 2 from the right, so I'm looking at this same x value right here. As I'm coming over here from the right side, what y value am I getting closer to as I get close to 2? +1. Okay, let's look at 4. So as we're looking at, as x approaches 4 from the left, as x approaches 4 from the left side over here, so 4 from the left side, what y value am I getting really, really close to? 3. As x approaches 4 from the right, so I got 4 right here, and I'm coming from this side, what y value am I getting really, really close to on my graph? 3. All right. As x approaches -4 from the left, that's a problem. When I look at -4 from the left, there's no graph over there. Let's say that does not exist, okay? There's no graph over there. Can't deal with it. As x approaches -4 from the right side, as x approaches -4 from the right side. So I'm looking at -4 right here, and I'm coming from the right side, getting closer and closer to 4. What's my y value? 2. Okay. All right, let's look at this. F of 2. If I were to plug in 2 for x, I'd get -1. Okay. While we're down here, f of -1, if I were to plug in -1 for x, plug in -1, I'd get 4. Okay. All right. So the limit as x approaches -1 from the left, -1 from the left side. So -1 from the left side, what y value am I getting really, really close to? 2. Now there's a dot up there. That would be my f of -1. But I'm not looking at f of -1. I'm looking at the number that it's getting really, really, really close to. Okay? So getting really, really close to -1, and my y value is going to be 2. As x approaches -1 from the right. As x approaches -1 from the right. So we're getting really, really close to this -1 from the right side. 2 again. Okay. We're going to hold off on these. Notice how all these are either from the left or from the right. Left or from the right. These are limits of just actual integers. And before we find those, I want to talk about when limits potentially don't exist. Okay? When limits don't exist. And so find this sheet of paper. There are 3 cases when limits do not exist. I'll give you a nice video to go along with this. Lindsay Lohan. There you go. First case, when a limit does not exist. The limits are different from left and right. Okay? So the limit would be different from the left and right. And I gave you an example right here. So x plus 1, absolute value of x plus 1. So we got a little piecewise function right here. And if I were to look at, the limit of -1, or as x approaches -1. So let's look at the limit as x approaches -1 from the left. And I guess we could write all that. Let's just write f of x. And then let's write the limit as x approaches -1 from the right of that function. Okay? So if I'm over here and I'm looking at x approaches -1 from the left side, what value of y am I getting really, really close to from the left? -1. If I look at it from the right side, so I'm looking at -1 right here, as x approaches it from the right side, I'm getting really, really close to +1. And -1 does not equal +1, okay? Not the same. Okay, so we can find the limit from the left, that's perfectly fine. We can find the limit from the right, that's perfectly fine. But if I wanted to write it as the limit as x approaches -1, just in general, that does not exist. Okay, next case, when limits do not exist, would be oscillating behavior. Man, I hope that's how you spell oscillating. I should have looked that up before I wrote that down. Oscillating behavior. That just means it's going back and forth, back and forth, back and forth. Okay. Justify why the limit does not exist for x equals 0. So we're looking at x equals 0 right here for this sine of 1 over x. So we're getting really, really close. The sine function is going to go back and forth. Okay. And the reason there's no limit as x approaches 0 here, so let's write that. Limit as x approaches 0 of this function does not exist. And you could say that however you want to. You could say because the y values are always changing. If you got on Desmos and kept zooming in on this, it would just continually be going back and forth the further you zoom in. I strongly encourage you to get on Desmos, graph this thing, zoom in at 0, 0, and just see that it just continually goes back and forth, back and forth, back and forth, okay? So, let's just say maybe the y values are constantly changing. Constant probably wasn't a good word. Constantly changing. Okay. However you want to phrase that. Third case, we've got where limits do not exist. Would be where it does not approach a finite number. Okay, so finite number that you can, count to. Over here, I'm looking at stuff, we did in behavior. In behavior would be like positive infinity. It's looking right here as we get closer and closer to, but that's not really a finite number. So that's kind of spoiler alert right there. Limit as x approaches 2 from the, why did I write -1? What a moron. The limit as x approaches 2 from the left. As x approaches 2 from the left, would be going to infinity. And the limit as x approaches 2 from the right, I didn't write f of x down there, equals positive infinity as well. But infinity isn't a finite number. So if we want to find the limit as x approaches 2 for f of x, that does not exist. Okay, it approaches infinity, it's not a finite number, that limit does not exist. So that leads me to, I'm hoping, yeah, there we go. On the back of this sheet, we got the limit existence theorem. And the limit existence theorem basically says, if the left limit is equal to the right limit, then the limit for that number exists. Okay? So let's write that in a fancy way. I'm going to write it all out and then I'll explain. Okay, I've got the limit as x approaches c of a function exists. Okay, so just a number, not from the left or the right. The limit as x approaches c of a function exists if and only if the limit from the left is equal to the limit from the right, and that's equal to a real number. Okay, so on the other side, we said, limits are different, left and right. We've got that. The limit is going to be equal to a number as long as left and right are equal. And then we kind of took the, the third one and said it's got to go to a real number here. Okay? Limit existence theorem. So let's take a step back. Let's go back to this. We started with this left and right hand limits. Let's go down here to the bottom and kind of finish this up. So I've got the limit as x approaches -1, not necessarily from the left or the right. If I look up here, I see that the limit as x approaches -1 from the left was equal to 2. The limit as x approaches -1 from the right equals 2. Therefore, it's going to be 2. The left and right ones are equal. It's a real number. So if I looked at the graph, as x approaches -1 from the left, it's getting really, really close to 2. As it approaches it from the right, it's getting really, really close to 2. Therefore, my limit is 2. As x approaches, let's do 0 first, this 0. All right, so let's look at 0. That would be right here, okay? X equals 0 is right there. And as we're coming from the left, we're getting really, really close to what, -1? As we're coming from the right, we're getting really, really close to -1. The left is equal to the right. It's a real number. The limit as x approaches 0 is -1. Let's look at approaching 1. Okay, so as we're approaching 1 is right here. Dotted lines are pretty crappy. As I'm coming from the left, we're approaching -2. As we're coming from the right, we're approaching -2. The left and the right are equal. It's a real number, -2. Now this last one, as x approaches 5, this graph, there's an arrow right there. So that means that my graph would continue going on and on and on like that. And so if I'm looking at this, my point right there at x equals 5, we're coming from the left, getting really, really close to -2. Coming from the right, we're getting really, really close to -2. I'd say -2. All right, let's slide back, do a couple more before we call it a day. So I'm looking at this limit existence one. If the left is equal to the right, it's a real number, so it's going to exist. All right, let's look at this graph. I've got the graph of f of x right here, and we're looking at all these to go with it. So I got the limit as x approaches -3. All right, -3 is right there, okay? Coming from the left side, right there, coming from the left, I'm getting really, really close to 0. Coming from the right side, getting close to -3, I'm getting really, really close to 0. 0 is a real number, 0. I guess I could have done this right here. -3 from the right. -3 from the right, we just said. We're getting really, really close to 0. Let's look at 4 right here. So 4 is right here, okay? As we're coming from the left, we don't really even have anything getting really, really close to 4. From the right, it would be -infinity, which is not a finite number. This one does not exist. As x approaches -6, so -6 is over here. There's -6. All right, what y value am I getting really, really close to? So from the left side, I'm getting really, really close to, what is that, -4? From the right side, I'm getting really, really close to -4. -4 is a real number, -4. Okay, as x approaches 3 from the left side, as x approaches 3, so there's 3, from the left side, it looks like I'm getting really, really close to -6 there. As x approaches -4 from the left side, -4, okay, so this is the -4 line over here. From the left side, I'm getting really, really close to -6. As x approaches -1 from the right side, -1, okay, so there's the -1 x line. And we want from the right side. So as we're going from the right side, it's getting closer to 2. 2. As x approaches 4 from the right, so as we're coming from the right side, looks like our graph is going to -infinity there. And -4 from the right, -4 from the right side, we're getting really, really close to, I don't know what that number is. Let's say -2.5. Okay. All right, lastly, let's look down here. Got this graph, f of x, and we've got these questions. So the limit as x approaches -3, okay? So we gotta look at -3 right here. And we were saying maybe from the left side, it's getting really, really close to, is that -6? And then from the right side, we're getting really, really close to -6 as well. Negative 6 is a real number. Negative 6. Okay. As x approaches 6, so 6 is over here. From the left side of the graph, we're getting really, really close to 0. From the right side of the graph, we're getting really, really close to 0. 0 is a real number, 0. All right, here's a weird one. As x approaches negative infinity. Remember end behavior stuff. So as x is going towards negative infinity, y is getting really, really close to, quote unquote, really, really close to positive infinity. As x approaches 1, there's the 1 line. From the left side, looks like we're getting really, really close to negative 2. From the right side, looks like we're getting really, really close to negative 2. Negative 2 is a real number. Does the limit as x approaches 3 of this function exist? Why or why not? So of 3, oh man, there's the hole. All right, x equals 3. From the left side, what am I getting really, really close to? 6. From the right side, I'm getting really, really close to 6. Does it exist? Yes. Why? Because the left limit equals the right limit, or the limit from the left is equal to the limit from the right. So let's say yes. Limit as x approaches 3 of that function equals, we said 6. Because limit as x approaches 3 from the left equals limit of x approaches 3 from the right. Ta-da!